Right, welcome to part two of this simple approach to the Mars challenge. So, in the previous video, we learned how to Kalman filter the data, the truth data, and we also learned how to compute features that will enable us to estimate the affine transformation matrix from frame 1 to frame 2. And this affine transformation matrix will be the data that we use to regress the vehicle speed from frame to frame. So that being said, let's actually collect this data, and I will go over the code to do that. So we're going to stream the video with OpenCV, and we're going to, didn't need to run that, I've already done this. So we're going to iterate through all the frames, and we're going to store the data in this X list. We're going to store the previous frame, and we're going to have a counter I. So for each iteration, we're going to store the previous frame as gray 1, and that's going to be and then right here we have the current frame is gray 2, and from that we're going to actually plug in gray 1 and gray 2 using our Sheet-to-Mossy method to compute flow that we saw in the previous video, and we're going to get this transformation matrix A, and you probably see A if we did a pass. So right here, this first part of this matrix is the rotation portion of the transformation. Now notice how these two values in the diagonals are close to 1, and these two values in the off diagonals are close to 0. And this is a very close to the identity matrix, meaning that we're essentially doing almost no rotation from frame to frame. And the second column right here is the translation vector. So we are doing this very small movements in the horizontal and vertical directions. So from frame 1 to frame 2, there is a very small movement in the horizontal and vertical directions, which is kind of what we would expect if the vehicle is actually moving. So we store that, and then we're going to do a transpose fatten. It doesn't really matter the orders as long as you're consistent when you store the data. So that's what we get. I've already done this, and I've already saved this off as a text file. So I've saved it as train X. We just get the 6-row, 6-column matrix with n rows, and I've actually added an extra row right here of zeros to compensate for the fact that we don't actually get anything for the first iteration. And in fact, in training, I actually removed that row and I removed that true speed data. So we do the same thing for the test video, just a different video right here. And now, this is just some formatting stuff right here. We have 8,100 samples for train and 6,100 samples for test. And once I drop off that first sample, we have 899 for the X and the Y train shape. And right here, I'm breaking, even though we have train, test, validation, I want to break these into different parts so I can actually test and validate my models on them. So we're using 80% for train and then 10% for validation and test. So this gives us this nice split right here. And I always like to use the random state to make sure I can follow my work in case I need to go back and do any rework and make sure things are consistent. So let's study the histograms of the training split only. So you can see in this rotation matrix, I have the diagonal terms right here, up and down. So they're both close to 1, and then the off diagonal terms are close to 0, which means we're roughly getting a identity rotation each time. And in the horizontal and vertical translation, you can see that most of these values are non-zero, meaning that we're going to have some form of translation from frame to frame. So what's more interesting is this histogram of the Y train. So the Y train is going to be, even though this is a smooth, Kalman filter smooth, we still have all these spiky modes. So these spiky modes correspond to times in the video where the measured speed and the truth data just freezes abruptly for no reason, and it's incorrectly freezing because the vehicle is obviously slowing down or speeding up in these cases. The only time where it's not incorrect is the 0, where when the vehicle stops, we can reasonably assume that the speed would be 0. So This is in the common filter video of how we can try to flag this. And in this case, we're not going to flag it and remove these modes from the training data. We're just going to train with them because even though they're not correct, they're approximately correct and probably good enough to train the models. So that being said, let's continue. So right here, so if you look closely at the data, you'll notice that the times where the vehicle is at 0 speed, this transformation matrix A is not always 0. And we might want to augment some perfectly 0 fine transformations for perfectly 0 speed. I've decided not to do that for the reason being is there's always stuff going on in the background that's going to cause noise to the speed. So I've decided to avoid that for this notebook. So let's prepare the data for training. So I'm going to use the standard scaler to normalize or standardize both the x and the y. And we do that using sklearn. And if we have a perfectly standardized data, we're going to have a mean of approximately 0, which is what we have, and a standard deviations of 1. So we've done that correctly, and we've also able to inverse the transformation. So we get the means, and then we do the inverse, and we get the same means. So that's just testing to see if it works. So now let's build some models, and let's see how to take this train data right here and predict the actual vehicle speed. So what we're doing here is I'm going to use a linear model, just a basic linear regression, support vector machine, a random forest, and a xgboost model. Now I'm using sklearn for the linear regression and support vector machine because it's easy. I'm using xgboost for random forest and xgboost. Any tree-based model I strongly recommend use xgboost. It's just as easy as sklearn, and it's also much faster and more efficient. So let's get started. So I'm going to import these. I've also tried a very simple, fully connected neural network. It did not work very well at all. I'm actually not even going to go through it because it takes a little bit of time to train. So let's fit these models right here. That's not good. Let's go through it right here. Let's load it. Okay. I think we're good now. Okay, now we're good. Had some variables I had overwritten. Just never good. So for the metric, I'm only looking at one metric in this video, and it's RMSE. I recommend you learn or look at more metrics if you're going to do this in a serious manner. So we can see that models get progressively better. The xgboost gets a 0.15 RMSE, but that's on the training data. So let's validate it and see how it works. And just real quickly, when I ran the neural network, you can see I got a 0.9. I'm not even going to try to tune it. We only have 6 variables. Neural networks usually work better when you have a lot of variables. So let's run the validation and see what we get. You can see we get about a 0.43 and a 0.47 for the random forest and xgboost. I've decided to go with xgboost, and I've actually decided not to fine-tune it for better performance, since this is just a baseline model and I don't want to spend a ton of time on it. I just want to get a quick estimate of how well I can do with as little effort as possible, so that when I compare more advanced models to it, I know whether I'm wasting my time with the advanced model or not. So let's go ahead and retrain with all the data. So I'm fitting everything right here. I'm redoing the standard scalars on the original data so I can make sure I use all the data for that. And now I'm going to get the training metrics. So with these training metrics, I'm getting the regular training predictions, but I'm also getting filtered training predictions. I'm going to see which one is different. So we actually get a little bit of performance boost, but you have to remember our truth data that we're using is common filtered. And I'm going to just go ahead and show the histograms of each one. So we have the true training speed, which is very spiky, has all the spiky modes. It's kind of hard to look at. Then we have our predicted training speed and our filtered training speed, which have roughly the same distribution. So let's go ahead and get our test predictions. We have our scalar test, and now we're going to get the predicted speed and the Kalman filter predicted speed. You can see we have some interesting modes right here that actually get knocked down once we filter them. So let's go ahead and look at the results. So in these results, I basically have videos of these. And here's the video of the training speed. So we have the true speed on top in green, the predicted speed in the middle, and on the bottom we have the filtered predicted speed. And you might notice that the filtered speed is a little bit laggy, and that's because of the Kalman filter. It makes it a little bit conservative and doesn't allow us to jump up or down too much. So that's all for this one. I hope you're able to learn how a little bit from the simple approach. That being said, I'll see you in the next one.